Here we are again. So we're looking now at forces on systems or connected objects. And we're still going to be using F equals ma. Nothing's changing there. But things are going to get a little bit more complicated. Because instead of having just one object that's being moved, we're going to have two or more. 3, 4, 5, 6, 7, infinity, whatever. We're going to have multiple things. And one of the ways we can think about this for connected objects is imagine that, you've got a box with like a string on it, and then this box is connected to another box, and this box is connected to another box. And you're pulling here. All the boxes are going to move together, right? Well, these three boxes connected together, they are a system of connected objects. And when we talk about connected objects in this classroom, we are going to assume that these boxes are held rigidly together. And what I mean by rigid is, I mean that there's not like springs holding these together. These are held together tightly, okay? If there were springs holding these together, then maybe when I pull the first box, it just like kind of moves on its own and the other boxes stay still. I don't want that. When I move one box, all of the boxes are moving. Likewise, if I had, two boxes together like this, and then I pushed them, both boxes would move to the right. And I wouldn't have a box like crumple on itself or do anything like that. The boxes are just going to move, okay? That's a very important feature that we are defining these as rigid systems. There's no like deformation or no stretching. They're just moving when you push or pull them. And that means we're using very strong chains or maybe ropes to do this, and the ropes are not deforming or stretching at all. In the real world, there is always some deformation and stretching and whatnot, but we're going to ignore that because if we use very strong things like metal chains, it's very, very minimal, okay? But everything's moving together in a rigid system. Now, when we go to set up these systems of forces for multiple objects here, one of the most important things we can do is write out a free body diagram for every single object. Each object will have its own free body diagram. That is imperative that you do this. If you do not do this, I can pretty much guarantee you that you're going to get a problem wrong. It's just what you need to do. You need to draw dots. You need to draw arrows from the dots. There's no way around that in physics. So, once we draw all those free body diagrams, we can set up some F equals ma equations just like before. Then we can start working through the math, which we'll see once we get into it. A little trick to it, but it's nothing you haven't done before. So let's take a look at this example here. What we've got is, as winter's coming, terrible ending of that show, by the way. You think it's a great time of the year to go ice fishing, despite global warming, and you'll fall through the ice. So you take your truck and you hitch your little camper RV to the back of it, and you head down the snowy, frictionless road. That's super dangerous to do that, but we made it frictionless just so we wouldn't have to worry about one more force, okay? Now, your truck itself, we'll call this MTR, has a mass of 174 kilograms. 2174, okay? And your big old diesel engine is pulling it forward with a force of 20,848 newtons. Now, you've connected your camper to the truck via the trailer hitch right here. Okay, and if you've ever done this, they're kind of a pain in the butt to kind of back up the truck and get the ball joint to fit just right, but if you do it enough times, you get used to it. And these are all nice and solid metal so that it's rigid, okay? So that's the connection. We also know that the mass of the camper, we'll call that MC camper, is only 437 kilograms because it's pretty much empty, right? It's just a box you're just pulling down the road. And we'd like to know two things in this. We'd like to know what is the acceleration of the camper, and then what's the tension in the trailer hitch, okay? Now, when we think about this, because these are rigidly connected, the acceleration of the camper is going to equal the acceleration of the truck. And we know this just from this basic idea. If the camper was accelerating at a greater rate than the truck, then at some point in time the camper would go through the truck. And I don't think your campers are going through your trucks. If for whatever reason the truck was accelerating faster than the camper, then the truck would be over here and the camper would be back here. And that's not happening either because we've hooked them together with a trailer hitch and they are rigidly connected. So what we can actually say here is since these accelerations are equal, we can just say that the acceleration of the camper and the truck, that is the acceleration of the system. And they're the same. Okay, whatever that number is, they are the same. And that's an important thing here. It's the same for both objects. So let's draw some free body diagrams and see what happens here. So here's the free body diagram for the truck. There's the dot. And here's the dot for the camper. Why don't you take a second here and you try to draw this free body diagram, and then we'll see where we can go with it. Okay, so let's check our free body diagrams here. The truck is clearly pulling to the left. That engine's doing its thing with that 20,848 newtons of force. Okay? But what is pulling the camper? Well, the camper is being pulled by the trailer hitch itself. So that trailer hitch is pulling to the left. That trailer hitch is not the 2848. That's one of the main things that students do the first time they do this. They say, oh, the truck force will be acting on the camper. But that truck engine is only acting on the truck. It's the hitch that's acting on the camper itself. And it's just pulling with a tension. We don't know what that tension is, but it is pulling. Now, this trailer hitch here, it's actually acting with tension in two different ways. If we think about like a little tug-of-war battle, here is the trailer hitch. While the camper is being pulled forward this way, if you think about it from the truck's perspective, or imagine that you're trying to pull the camper, if you put a rope on your back or like a harness to the camper and you try to run forward, that camper's it's gonna tug you back as well. So while you're pulling it forward, it's pulling you back with that same tension. This is a Newton's third law here. These tensions are equal and opposite, okay? So both of these tensions are here. They're technically the same tension, but in opposite directions. That's an action-reaction pair of Newton's third law. And because it's frictionless, that's it. That is all we have in this problem. I don't know what these tensions are. That's actually part B, but we'll see how we can get them, okay? Because we have these two free body diagrams, we can actually now go ahead and solve this problem. And the way we do this for all these force problems is F equals ma. The sum of the forces equals a mass multiplied by an acceleration. And the way we're going to do this is we're going to do this for each free body diagram. Some people, like myself, I like to draw little circles around my free body diagram, so I know when I'm applying my F equals ma equation, I'm only applying it to the forces that I drew the circle around. So for our first equation here, I've got the 2848 and T for the tension. My second equation will only have a tension. And one of the first things I really need to do is I need to pick a positive and a negative direction. It doesn't matter which direction you pick as positive. You just need to pick one. We're actually going to pick left to be positive here and right to be negative. I know that's a little weird. That's like backwards from your math classes, but everything will be fine. Nothing will, be destroyed. The world will still exist. So if I write F equals ma for my left equation, I'm going to have a positive 2848 because that's the positive direction. So 2848 plus negative tension because it's acting to the right. So that's minus tension equals the mass of the truck, which is 2174, multiplied by the acceleration of the system. If I go to the right side, I only have a tension. It's positive. That positive tension's over here. So tension, that's my only force, equals the mass of the camper, 437, multiplied by the acceleration. Now, if we look at these equations here, I don't have the tension and I don't have the acceleration, which is a huge issue because if I'm looking at this equation, how can I solve if I have two unknowns? Well, if I have two unknowns, I can't solve them with just one equation. I need a new equation for every unknown I have, which is nice because I've got one equation and two equations. So I've got two unknowns. That means I have two equations, which we've written, and that means I can solve this. What we're actually going to do is notice that these tensions are the same. Since they're the same, we could use a substitution method. I'm going to take the 437A, the accelerations, and I'm going to move them over into the tension because that's what they're equal to. And by doing this substitution method, I'm actually going to be able to solve for acceleration here. So if I do this, we'll have 2848 minus 437A equals 2174A. Now we can combine like terms. These are like terms here. Notice that the negative right here, that negative stayed because it was just the negative in the equation. So I'm going to simply add 437A to each side. That goes away. We get 2848 equals 2611A. And then to solve for A, we simply divide by 2,611. And that will give us an acceleration of 7.98 meters per second squared. And you know it has to be meters per second squared because it's an acceleration there, okay? So that's how we can go and use these two equations for our free body diagrams, our F equals ma, and then use a substitution method to link them together to find the acceleration. And remember, this is the acceleration of the system. It's the acceleration of the camper, and it's the acceleration of the truck. Now, we're not really technically done with this problem yet. We still got part B. Part B is asking, what is the tension in the trailer hitch? Well, how can we do that? This is actually really straightforward. We know the tension is right here. It's just 437 times A. We now know A. Let's just plug it in. We could have also plugged it in over here. There's a little bit of algebra to solve it. I don't want to do more math, so let's just use this one. So we can just say that tension equals 437 times 7.98. Mass times an acceleration will give me a Newton, which is a unit of force. So 437 times 7.98 gives me, just approximately 3,487 newtons of force. Okay? And that's it. That's our whole problem. We're done there. We are finished. Nothing too crazy. The biggest things about this are recognizing, hey, I have two objects. I should be drawing two free body diagrams. And then once you do that, you can create an F equals ma equation for both of them. And then if you see that you can link them together, you can start doing that substitution math, which is math you've done in the past. It's just now we're actually putting it to use outside of a math classroom. Okay? So nothing too crazy, just more F equals ma. This is kind of like the peak of where this unit is for right now. Okay?